So that's our task for today. So maybe that's set the stage. The fact that what you would have seen on Monday was this idea that it's really not very different from what we've looked at before, and that is that we have a stream tube that maybe has something in the middle of it that we can write between an upstream and a downstream location. And I guess the sign convention is important that it is upstream and it is downstream for each of these relationships. And it really doesn't look any different from what we've dealt with before. You'll see all of the components of Bernoulli upstream, all of the components of Bernoulli downstream. It differs only in this term here, alpha 1. Alpha 1 very straightforwardly is just is a term that allows us to say something about the form of the flow velocity that occurs. And if the flow velocity is absolutely uniform within the stream tube, then alpha is equal to 1. If it's not, then it's less than 1. And so if it looks something maybe like this, then this value of alpha would be less than 1. So it's just a term that relates to the distribution of flow across this face of the stream tube. But other than that, this is Bernoulli 1 upstream, important, and downstream. And there are two extra terms. One that defines energy put into the system by a pump, and this is HP is positive if it's a pump, negative if it's a turbine. Turbine is just a pump in reverse, right? Spins because the water's moving it and it pulls energy out of the system. And it can be defined in terms of this relationship here. This is pump head is equal to power, joules per second, or watts, hence the rate of doing energy, divided by mass flow rate times G. You can do it as power per unit mass flow rate if you divide this expression top and bottom by mg. So in other words, power, which we've called large W, is equal to per unit power per unit mass rate divided by mass rate, right? Is that, no, it's the other way around, isn't it? Forget what I'm doing here. Yeah, by definition. So this is power per mass flow rate, and so we can define that. So just by definition. And it always conforms to this sign convention. Likewise, the head loss is always positive. And physically, I guess what it might mean is if I come down here and attempt to draw a diagram that relates these, this is along the streamline. And so what this physically means is that if you take what would be a magnitude which is constant, we often think of this as the energy grade line. All that this physically means is that there's some head loss, which is losing energy as you flow down a pipe because there are these frictional losses. And that we could, for instance, we could look at this as being, well, relative to some point, this is Z, this is P over gamma fluid, and this is v squared over 2g at the upstream location and also at the downstream location, and there'd be some distribution of these same things here. So this would be v2 squared over 2g, this would be p over unit weight of fluid, and this would be the elevation of this point. And so this is Bernoulli, written in terms of these three terms. It is a magnitude. We think that it should be constant, so the energy grade line should be constant. But in the presence of head losses, it means as we go downstream, because as we go along this pipe, there is some shear forces due to viscosity on the side of the flow as we go down. There's some head loss that comes out of this. And we can define this in terms of the appropriate units, some coefficient, usually between 0 and 1, v squared over 2g, that allows us to be able to translate this into behavior along a pipe. So not next week, but the week after, week 10, we'll talk about pipe flow. And the essence of pipe flow is how do we figure out exactly what this head loss is as a function of the diameter of the pipe, the roughness of the pipe, the viscosity of the fluid that's flowing, and how do we establish rules for that so that we can use it to do appropriate calculations for this straightforward energy equation. So this energy equation is no different from conservation of momentum along a streamline. Conservation of momentum assumes that there are no losses in the system, but we have losses due to us just putting in a parameter that does that. If we were to draw out what this would look like in terms of this pump, I suppose this little energy diagram would look something like, I'm just going to do a separate diagram because it'll get confused otherwise. So this is still S, this is still 2, and this is 1. So you can imagine that this component here would be Z1 plus pressure head plus velocity 1 squared over 2g. And what a pump would do, you could imagine it as being something that if you have a pump in your circuit, then it puts in some amount, which is this. And now all of a sudden this amount is Z1 P over gamma, P2 over gamma, and V2 squared over 2G. And if we want to, we don't really care what this looks like, we'd probably think of it more like this, right? So a pump head is given by this idea here, and that's just this term. So in this case, a pump is adding head to the system, juicing up the system if you like. If this is negative, then you're taking energy out of the system, so it would be on a decline, but that's basically the ideas. So these energy equations are just written along a streamline, as we've alluded to here, and they're written in two slightly different forms. You'll see that the kind of, one is a physical equation, if you like, for all the components that we've talked about. One has these chemical components, so you can put chemical energy into the system. And you'll see they're similar. This is the v squared over 2g term. This is the elevation head term. And this is the pressure head term. The mass flow rate is always positive. But this term, H, is enthalpy. And instead of just being equal, and it's not equal to the same head that we're talking about here, and it's equal to internal energy per unit mass plus, I think, pressure divided by density. So the pressure head term still exists in here, but it's supplemented by chemical energy or enthalpy in the system, which can be transformed. So it's just written in a slightly different way. This is thermal energy positive into the system, rates of thermal energy into the system, and this is rates of work into the system in terms of pumping, the same expressions as these, but they're used in slightly different circumstances. I think at the end of the stuff on Monday, we talked about using this expression to solve for steam turbines, etc. But most of the stuff that we'll do will be in the form of this physical expression here. So that's it. So that's kind of a recap of these. One for chemical behavior, one physical behavior. Along a streamline, all we're allowing now is the fact that now we're allowing losses of energy and energy input into the system. Obviously, you could take this pump and take it out to the other side, and it would be HL minus P. And you can see the difference in sign of those things corresponding to the different behaviors. But this is a useful idea to have in your mind of physically what this means. And that is that a pump adds energy into the system, and frictional losses along a pipe means that you lose energy as you go from upstream to downstream. And I suppose, technically speaking, the energy grade line should probably be this, right? This is just the constant value. So this is const. This is the fact that Bernoulli between upstream and downstream can be written as equal to each other, the two behaviors, and so it remains constant. So the other thing, it is important to remember these sign conventions. It is in the other Bernoullis, it doesn't matter if you write upstream as 1 or 2, but it really does in these cases that you're mindful of the upstream, which is in, and the downstream, which is out, and likewise here. It's okay. All right? So, what we do. So maybe today we'll try and do a couple of things. Let's do a couple of examples, and then what we will then do is we'll try and do this differential analysis. And specifically, if you're an environmental systems engineer or petroleum engineer, and other engineers in the programs in our department as well, certainly you'll deal with porous medium flows, where the whole essence of the porous medium flow is that in pushing stuff through gas shales or reservoir rocks or aquifers, you lose head by friction along the sides of pores. Think of a porous medium, just as the in-grain example, as a whole series of capillary tubes. As you flow from upstream to downstream, you lose energy, you lose head, and the whole essence of that head loss is what is defined as permeability. Okay, so hopefully we'll get to that. All right. So, couple of examples. So these are from the book. I presume they still exist in the current version. So you have two reservoirs, an upstream reservoir and a downstream reservoir. The flow is in this direction, so that defines upstream and downstream. So it's not so much the lower versus the higher reservoir. I guess that's worth defining. There's a difference in elevation between, which we know. There's a frictional head loss in the piping, which is given by this amount here. So in other words, HL is equal to this rate times V squared over 2G. There's this Darcy-Weibach equation that we had here, pardon me. And this is just a constant, a dimensionless number, right? This is units of length. We know that this is also units of length. You have to be careful that this is the velocity defined somewhere. The velocity in these big tanks is 0 probably because they're big compared to the pipe, but this is the velocity within the pipe. And there's also a pump within the system. So there's a head loss in the system, and there's also a pump in the system, and we define the pump as being equal to the power divided by the mass flow rate times gravity. And there's we know what KL is, goes in here. So this is 20. The relation between the total head rise across the pump and flow rate Q through the pump is given in this expression here. So this is the pump head HP. And I guess we don't have to define it in these terms. This equation for pump head, if we write it out, is going to give us, for 0 flow rate, it gives a big head. It's basically saying that the pump, if it's not delivering very much fluid, it can be very strong. If it's delivering rate flat out, then the pressure that it adds to the system is very small. And so the equation of this pump head is something that at 0, it delivers 200 feet of water, and at 2 cubic feet per second, it delivers 0 feet of water. And so the expression that defines that is just this. Where Q is equal to 0, it equals 2 times 100. Where Q is equal to 2, it's 2 minus 2, which is 0 times 100, which is 0. So it just gives you these end ordinates, and also gives you a linear distribution in between. So we can write our relationship between upstream Bernoulli, downstream Bernoulli. Pump in the system is positive if it's in, and head loss is always positive by definition. You can't have a loss in any system, so sign convention is always positive. So if we write our equations between upstream and downstream, atmospheric pressure on both of those boundaries. Big tank assumption means that the velocity on this surface compared to in the pipe is 0. So get rid of those. And the elevation is that this one would be 0, I suppose. And this one would be plus 100. 100 feet in this particular case. And so then we just have to add into here the fact that we have HP is equal to 100, 2 minus Q, well, and this is in units. This has to be in units of, it's not dimensionless, right? It has to be in units of cubic feet per second. And if you do that, then it comes out to be units of feet in this particular case, so we have to be careful of that. And I guess we have to use the fact that this here is equal to KL, which I think is 20, V squared over 2G. This is 20, and V has to be the mass flow rate. And so I guess V has to equal Q over the cross-sectional area of the pipe. So this is for the pipe. So in other words, we have an expression now which identifies something in terms of Q in this term. The term for these is just Z1 minus Z2, which is in length of feet. And we have this also defined in terms of volumetric flow rate. So V squared is equal to this. This has to be pi d squared upon 4. Do we have the diameter of the pipe? 4 inches. And so you have everything you can to calculate that. So you have one equation. It's written only in terms of Q in this term, Q in this term, and a length difference between Z1 and Z2 that you have. And you can solve for, it's not so easy because you end up with a quadratic equation that you have to solve for the roots of. So you have two potential flow rates, one of which may be negative, I'm guessing. And you take the positive one of which is non-physical. So usually that's the way. So that's it. So you just have to figure out exactly what you substitute into the right places. Right? Straightforward enough. Same idea here. Using, I guess, a slightly different form of the equation. Well, let's talk about the question first. So you have gasoline going from upstream to downstream. It's piped along a pipe, goes in here, comes out here. We know that the unit weight of gasoline is equal to Sg times the unit weight of water. Don't know why we need that, but I guess we know that water is 1,000 kilograms per cubic meter, or 9.81 kilonewtons per meter cubed, I guess, for unit weight. We know the flow rate is Q from this. We know a head loss between these two is this, which is equal to 0.3 V squared over 2. It's the velocity at section 1, I guess. And the unusual thing is that's given here is there is no g here, so it's a bit misleading. This, to be dimensionally consistent, for this to be truly a head loss, this has to be v squared over 2g, because otherwise it's not units of length. And so here we have to be careful that this is not quite a head loss in the system. And you're asked to find the difference in pressures between 1 and 2 if there's this amount of energy that's being put into the system, which is power. So this is what we'd call uppercase W dot in watts, joules per second. Yes?
Could you rewrite the thing all the way on the right here?
Can you not see it? Is it off the board?
Yeah.
Is it on the board now?
Maybe a little bit that way.
Oh, that's on the left, isn't it?
I don't know. It's hard to.
You're missing the Q?
Yeah, there you go.
Yes, that's your left, isn't it? Yeah. It's okay. No, he's translating it because he thinks it's on my right because we're facing each other. But no, it's on my left too. So I have to think about that. So yeah, so you have to be a little careful about the definitions of here. And so this is, so we can write it. Have you got it? Can I make it bigger again? Because I can't actually move it so easily. So, is that I know you lose some of this. You lost P1. All right. So I'll write it here as HL is equal to 0.3 V1 squared over 2, which doesn't have this G attached to it. So we have to, it's not clearly not a head loss. So the same approach as before. Bernoulli between the upstream, the downstream, pump in and pump out. So this is Bernoulli. So this term here is actually HP, which is equal to uppercase W over Q rho G, I think. And so if we look at that, we can define this is, if we can define this as lowercase w dot over G, if you remember. Right? This term that I'm outlining here is power per unit mass flow rate, Q times density, right? And so this is power per unit mass flow rate. So that's all that's different here. And this is a head loss. So here, what's happened? I guess we've multiplied both sides of this whole term here by rho G, because this term here all of a sudden loses this. So if we do that, we've lost the density. We have a density divided by gravity, so we have density here on the outside and just v squared over 2 because gravity's lost. And we need to take this G here, rho G Z on the outside, and it's etc., and we've lost this. And so that's just the same expression that's just written in a different way by multiplying through by density times gravity. We lose these different terms here. And then instead of writing it on either side of the zero, we write it in terms directly of what we want to find. And what we want to find is the difference in pressures between upstream and downstream. Upstream has to be location 1. Downstream has to be location 2. And so this is what we want to calculate. These are the other terms that we know, or hope we know. We certainly know the difference in elevation. Z2 minus Z1 is going to be 3 meters. Right? This is 3 meters. This is 0 meters. The velocity is upstream. I think there are different cross-sectional areas, right? So different D2s. And so we do know the flow rate here. So we know that Q is equal to V1 times A1, which is equal to V2 times A2. And so I suppose we can write both of these terms in terms of that. So we can get V2 is equal to Q over A2, and we can also get V1 as equal to Q over A1. Right? Both of these terms. So presumably, if we know the flow rate, and we do, and we know the cross-sectional areas, which we do, we know the diameters, we can certainly calculate what each of these are. So we have those. We have these. We have a loss within the system, which we've been told is equal to K V1 squared over 2. We know that V1 is equal to Q over A1. So we definitely know this term here to go in here. And we know that this term here we can define in terms of the individual components. So what do we know about lowercase w dot in is the same as this term here over density, it's density not P, density flow rate times G, right? So this term here is just these components here. And what do we know? We know that uppercase W is equal to 20 times 10 to the 3 watts. Which are those units there. And we know that Q, well, we've been given Q. We have Q here. We have Q, we have the density, which is equal to specific gravity of gasoline multiplied by the density of water. And so we have this. And we have G is equal to 9.81. So I won't bore you with the calculations, but basically we want to know what this is. We have a density of gasoline, which is this here. We have the difference in velocities between upstream that we can calculate just from continuity and knowing what the flow rate is. So we have these. We have the elevation difference between upstream minus subtracted from downstream. We have this amount here, which we know is 20 kilowatts divided by mass flow rate in G. And we have this loss here. And if we plug and chug, then we should be able to calculate what the pressure difference between upstream and downstream is. And so in this case, the pressure at point 1 is less than the pressure at 2 because this is negative. And that kind of makes sense because of the diagram that we drew before is, well, is there enough space up here? Not really. The diagram we drew before, schematically, this is our pump between upstream and downstream, and this is HP. We said before that basically what we're doing is we start off here, and this is basically HP that we've added. So this is point 2 downstream, this is point 1 which is upstream, and so not surprisingly this pressure here is lower than this, and so when you subtract one from the other you get a negative value. So in other words, this would not flow. It only flows because you're putting some energy into the system, which is this amount that goes in here. Where it's lowercase w or uppercase w, it's just a different way of writing it. Okay, so those are the kind of solutions to get. How are we doing? Fine. I'm not going to. Well, energy is also recovered that way. So pumped hydro and hydro schemes. The idea is that you run water through a turbine. It turns the turbine and adds work into the turbine, which is that this is negative. So turbine is negative when we look at the Bernoulli equation. If when you collect water here, you pump it back into the reservoir, so-called pump storage schemes. One of the big issues with renewable energy is its intermittency. You get power when the sun shines or when the wind blows, but you need to even it out for demand, and you need to store it at night when it's not used. And so one way you can do that is you can pump water up the hill so it has some potential energy, and then you run it back through the system after the fact. So here the question is, what's the maximum power that you get out of the turbine that you showed here? Again, Bernoulli upstream, Bernoulli downstream. We have to write them appropriately at the upstream and downstream locations. In this case, what's the maximum you get out of it? The maximum is when the head losses in the system are zero. In other words, you'd lose some head loss in the piping that brings, sometimes the reservoir is not connected to the turbine except by a tunnel, a head race, which enters water at high speed into the tunnel. And there are friction losses along that. But if the friction losses are zero, then we can calculate what the maximum power would be. If you write out the pressures at these points, zero upstream and downstream, for the same idea as the jet engine where this squirts out of the water, it's atmospheric. Velocity upstream is zero because of the big tank approximation. The velocity downstream is not zero. This is 6 meters a second. If it went into a big lake, for instance, it could be zero, but that's not the case here. And the elevation difference between these two things is given by these two components here. So in this case, it's 50 meters. And the only other term that we have left over is this term here, which is going to be the power divided by the volumetric flow rate and the density of water is equal to HP. And we have to realize that it's positive for a pump and it's negative for a turbine. So when we go through these, we end up, in this case, actually it's convenient to do it in terms of lowercase w. This is lowercase w, because it's equal to, then you don't need to know the flow rate. You could calculate the flow rate here, but this is power per unit mass flow rate, so it's just simpler. And it comes out directly as the velocity, the difference in heads, which is 50 meters. This is zero, and you can calculate the mass. And if you pump water back in, so obviously if there's a loss here, then you reduce the power that you get out of the system. If there's a loss here when you pump it out, then the same when you pump it back into pump storage, you have to accommodate, you don't gain it, that loss is still there. The loss is always positive. And so you lose energy when you convert from potential energy to electrical energy as you run it through a turbine because of the losses in the pipe and the conversion losses. And when you run the turbine as a pump to pump it back to this higher level, you also lose it again. It's the same as friction. I always use the example, friction acts against you. I pull the bag towards me, I have to put energy in to pull it here. To get it back to the same position, it doesn't go there automatically. I have to put the same amount of energy against friction to move it back. So you lose it both when you pump, convert from potential to power, and you lose also when you put it in the battery to send it up to the top of the system. Okay. All right. Do we have enough time? Yeah, actually. So, yeah, all right. I was going to do something else. I still am going to do something else, I think. Oh, I didn't get rid of this. All right. Well, I guess I can just go to the next figure. All right. So the other thing that we might want to look at is in this is to go back to those figures that we were talking about before. And so we're looking at conservation of energy in this particular case. And we are 8.2, right? And so in the systems that we've looked at before, so we've done this. I like this figure. This is our Bernoulli. This is how we've done it. It's always been behavior along a streamline, and looking at the different other components that exist across here. So one thing we could do is that on our way to look at conservation of energy, we made the point that in looking at these complicated simulations of water flowing and jumping around all over the place, we need to solve two systems. The first is conservation of mass, and the second is conservation of momentum, or we could say / energy. And we've made the point already, and it's worthwhile noting, is the conservation of momentum equation we have, this is Bernoulli. And conservation of energy is Bernoulli plus HP and HL. So that's the only difference for these things. You can think of changes in momentum as changes in kinetic energy in some respects. And so the only difference between the system that we've dealt with before is that in adding to Bernoulli, we want to have the fact that we can have losses in the system by viscosity along pipes or along the channels that water flows through. And we could put energy into the system, which is just the reciprocal of losses. And so maybe it's not surprising that when we look at these behaviors of characteristic systems, is that still on the figure, by the way? Yeah, I guess you've lost an A and a V off the right side of this. Is that instead of using a stream tube, that's a squeaky chair, is we can come back to use our friend that's off the screen as well, isn't it? Yeah. So do this. And so we can describe this would be dy, dx, and dz. And what we might like to do is, if we look at this first expression first, we define conservation of mass. And that is that we had rate of change of density and volume plus sum of mass flow rates are equal to 0. And typically we've written this out in longhand on the left hand side to have two parts. Density times the rate of change of volume plus volume times the rate of change of density plus mass flow rates are equal to 0. And if the control volume doesn't change, then this is equal to 0, and we have these two parts. We have the mass conservation part, and we have the accumulation part. This just says how quickly it accumulates. This says mass in equals mass out, then it's equal to 0. If there's some net accumulation, because fluid goes in and less fluid comes out than goes in, then its density has to change, even though the volume is the same. And so this is the accumulation part. And so what we can do is we can write this in terms of a velocity in the y direction that goes in here, a velocity in the y direction that comes out of here, which is dv dy times dy. And if we write sum of mass flow rates is equal to 0, then we can write this as the area times the density times v, right? And so in terms of that, the area is dz times dx, right? This, the area of this face here, is multiplied by density. And the velocities are, in is minus Vy, because of our sign convention. Flow rates in are negative, and flow rates out are Vy plus d Vy dy times dy. And so if we look at this and this, and write that out in longhand, and this is equal to 0, which is also equal to the sum of mass flow rates, is equal to dx dy dz, I'm taking this d here, times density times change in velocity in the y direction with y. And this is the sum of mass flow rates in the y direction. If we realize that we have to do these in all directions, then the sum of mass, these are all in the y direction, then the sum of mass flow rates in all directions are going to be equal to this term here. I guess this is volume by definition. And so if we do it for the other two components, which are in y and z, then we end up with volume of the control volume, density, and I'm going to do as a partial, velocity in the x direction dx, plus velocity in the y direction dy, plus velocity in the z direction dz. So this is sometimes called the continuity equation. It's certainly a mass conservation equation, and this can be equal to 0 so long as there's no accumulation. And so what we might do, and I'm going to actually do one that continues this next time because we're kind of out of time. What we could do is we could look at exactly what this conservation term here should be for accumulation. And then what we'll end up is with the basic expression that you start off in all of your reservoir engineering courses or all of your groundwater hydrology courses, is a groundwater flow equation or flow equation which has an accumulation term, which is storage or compressibility of the gas, and a conservation term which is mass in equals mass out, that comes from this. And so let's save that excitement for Friday and we'll deal with that. Okay. All right.